alkene, transalkene. But now if you have to differentiate these things, let's say this hydrogen and these things, then we will see how NMR spectroscopy is helping us. By using NMR spectroscopy, we can fantastically differentiate these two conformations. Okay, we'll have a look on that. Okay, so let's say we have this kind of skeletons, H. So how this proton nucleus is going to interact with this proton nucleus, that we'll see now. Basically, we can imagine it depends on dihedral angle. Dihedral angle. So now, can we imagine or visualize the dihedral angle? Of course, yes. Let's say you have a book. You open the book, not completely, partially. So it's open now. Now on that, in the middle junction of two pages, you have that CC bonds. So one CC bond lie in one page, another CC bond lie, so not CC bond, CC bond lie on the junction of the book. So one CH bond lie in one page, another CH bond is lie another page. The situation is like that. Let's say this is the book. This is the book. This is the junction. We have these CC bonds. Here we have one CH bonds. Let's just write quite better. Okay. This is the book. This is the junctions. Here. So this is lying this CC bond on the junctions. Here we have these CH bonds on this page and we have this page. And just you can do also these things. Okay. Now the picture looks okay. So this is the book we have opened, and here we have put the CC bonds on the middle junctions. One CH bond this page and the CH bond this page. Then this angle is said to have dihedral angle. Dihedral angle. So if the dihedral angle is 180 degree, let's say for this kind of system, look, the book is completely opened. The dihedral angle is 180 degree. Then the coupling constant is quite more because it's parallel alignment. That's what we have learned. If the dihedral angle is 180 degree, then we'll have parallel alignment between these bonds, this one, and this one. They align parallelly. So parallel alignment. So if the dihedral angle is 180 degree, there will be strong coupling, and the coupling constant value will be around 10 to 12 hertz. So in case of these things, look, the dihedral angle is like 60 degree. Okay. Then we'll have no parallel alignment, not parallel alignment, because one bond is projected this direction, another bond is projected this direction, so not parallel alignment. So coupling will be weak, and coupling constant set to a value like 2 to 3 hertz. 2 to 3 that we learned. So in case of on the dihedral 180 degree, this is a parallel overlap, not overlap alignment. We have stronger coupling, higher J value. Weaker coupling, lower J value. We'll use this thing to explain these things. We need this data. So what is happening here? I will draw both the structure parallelly. We have here H, H, and in this case, this is one OH is here. This is one OH, H. Okay. So yeah. So in both case, each protons, whether it has been placed equatorial or axial, have similar CH2 environment. Okay. In both cases, here see these protons get one CH as axial and one in equatorial. Here also this is getting one CH is axial, one is equatorial. Same environment. So in both cases we have two identical neighbor in both cases. So this is what we are going to get. See here also we have two neighbors, similar identical neighbor here also for these protons. But what the difference? This is projected axially, this is projected equal. So here will be a coupling. Here coupling is equatorial axial. This proton will couple equatorial with this and axial with this. So here we have equatorial means it's equatorial with these things, is equatorial with these things, it axial with these things, axial with these things. Here we have equatorial and axial coupling. So these two couplings from the dihedral values, we know that for equatorial it is quite less. So less stronger this coupling. One thing we found out, the coupling, what is happening in this environment is less stronger. But here we have axial, equatorial. Okay, for these protons. Here we have axial, equatorial, means axial, equatorial, and axial, coupling. And from the dihedral valve, we know that this kind of axial coupling is stronger. So quite comparatively stronger coupling that we find. Stronger coupling. Then what type of splitting will happen? One thing we decide, this coupling is stronger here, this is lesser here. Basically it's a, see, this will be coupled by some CH2 triplet, again each CH2 is going to couple by triplet manner. So this is a triplet of triplet. It's triplet of triplet. Same thing here also, triplet of triplet. So triplet of triplet. If this is triplet of triplet and less stronger coupling, then the triplet of triplet means we have 9 peaks. 9 peaks will be concise, will appear in very concise manner. Just think you have a 9 peak here. This will appear in very concise manner because this determines the coupling. This period is very low coupling value. This is not the coupling constant, but it is spread very concisely. And this is stronger coupling is here. So here 9 peak will appear in more separated. So this is more concise, more concise or more compact. This is one proton, more compact. As weaker coupling, as weaker coupling, this is less compact. As stronger coupling, stronger coupling. So just identify which proton is there. Just identify the triplet of triplet and see its spreading region. If it's spread over large region, that appears from the stronger coupling, which is because of this kind of axial, this axial, and axial equatorial, means axial equatorial. It will be spread over larger region. Here it is equatorial axial. It's quite weak as coupling. That's why it's spread over very concise region. So seeing the or identifying the spectrum first and then seeing the observing the nature, we can easily say whether this is this one or this one. Provided we have to know this fantastic phenomenon. The couplings depend on dihedral angle. Okay. So up to this, what we have learned, again I am concising diortho or dimeter. Yeah, we can do it by NMR. Cis or trans, we can do it by NMR. Axial equatorial, we can do by NMR. Then what's more? What next? Let's say we have these things. Yeah. And yes, this one. This is oxygen and this one. And we have these ones. So basically we have two oxygen here and one here, H. So how to identify? Very simple things. Here we have axial coupling as the orbital aligned parallelly. Axial coupling more or stronger, larger J value. Here these two orbitals are not aligned parallelly because of their parallel alignment. So not aligned in parallel. That's why weaker coupling. Another thing we can say means or small dihedral angle, small dihedral angle. As a result, weaker coupling. We will have very low coupling constant values. Between those, we will have doublet where we have more J values. It means it's from these conformations. Where it is less, it is from this conformation. Look, here the value is around 7 hertz and here it is very much low. So orbital alignments matters a lot as coupling works through bond. Here it is J is equal to 1.3 hertz. So we can differentiate this kind of conformation also by coupling. Okay. So always dihedral angle matters is no, because if I show you these kind of things. Yeah. So they are on the same plane, same diet triangle. Look, here don't have any chain diet triangle because they are projected on the same page of the book. It's 5 member, then come the 6 member, and so on. And you can with 7 member also. Yeah. Then how to detect them by NMR? Very interesting. Because here the diagonal angle is same. They are projected on the same page of the papers. Then how? The answer is look here. These two hydrogen, because of this kind of ring state, are projected from just quite apart. Here, quite closer, again more closer, more closer. The look, the bond become more closer. Sorry, more at distance. Here, quite closer. Again, the bond become closer, closer. Means as the coupling is a through bond effect, these bonds are becoming closer from this to this. That's why gradual increase in coupling constant. As the bond become closer to each other, there will be more coupling, stronger coupling. As two siege bonds are becoming closer to each other, we will have more stronger coupling. As this is working through bonds, interest will be better. So that's why here the value is 0.52, 1.5. For this case, it will be like 2.52, 4.0, 4.0, and here it will be like 4 to 5, it is 5 to 7, and it is 8.5 to 11 in cis coupling. That's things. Or you can say one thing that it is much better to again say, of course, the bond becoming closer. That's why we will have better overlap. So what is happening once the bond become more closer? Why became the bond become why the as the two cis bonds are becoming closer to each other, more stronger coupling happen. This is why this is happening. That's we can clarify. See, the bond is projected here in this direction. This is these directions. Look, if we say this is the bond, cis bond, these directions, these directions. Once this is 4 member, look the bond, these directions. So with increasing the ring size, the bond is gradually the CH2 CH orbitals are gradually becoming quite parallel. See, here they are far more deviation from parallel alignment. Here it is towards parallel elements. That's why it is going to happen. That's why their corresponding J value is going to increase. So by studying NMR spectroscopy, we can differentiate these kind of things also. That is, in conclusion, as the ring strain decreases, the two CH bonding orbitals become more closer. As a result, their parallel like alignment increases. I am not telling here also is not parallel, but it is closer to parallel. It is far from parallel. That's why their parallel like arrangement is going to increase. Means we have much more